Did you know that out there in the vast darkness of the night, a galaxy is racing toward us at nearly 400,000 kilometers per hour? A kind of parallel universe, 2.5 million light-years away, yet with every second, every minute, it is drawing closer to our Milky Way. So take a seat, or lie down if you like. Let your shoulders soften. Take a deep breath in, then let it out slowly. Tonight, we are going to travel together to a distant world that feels strangely familiar, the Andromeda Galaxy, our greatest neighbor in the cosmos. This is not just a journey through space, but a journey through time, through the memory of the universe, through the questions humanity has asked, and continues to ask, about the nature of existence itself. If what I share with you tonight brings a little peace, a spark of curiosity, or simply helps you relax before falling asleep, I would be truly grateful if you took a moment to like the video and subscribe to the channel. It is not just support, it is a way for us to build a community of people who love science, who love the universe, and who believe that knowledge can arrive gently, like a whisper in the dark. Andromeda is a name born from Greek mythology, the story of a princess chained to a rock as a sacrifice to a sea monster. But tonight, we are not telling a myth. Tonight, we are telling a story that is more real, more wondrous, a story about a galaxy holding more than 1 trillion stars, about a supermassive black hole 100 million times the mass of our Sun, about light that has traveled for 2.5 million years just to reach your retina when you lift your eyes to the night sky. According to observations from the Hubble Space Telescope, Andromeda spans roughly 220,000 light-years across. Compared to our own Milky Way, which measures only about 100,000 light-years, Andromeda is a colossal older sibling. It is not only larger in size, but also richer in stars, an estimated 1 trillion of them, compared to the Milky Way's 200 to 400 billion. When you look at Andromeda from Earth, you see it at a slight tilt. It is a spiral galaxy, much like the Milky Way, with sweeping arms stretching outward from a bright central core. In images captured by modern telescopes, Andromeda appears as a vast spinning disk, woven with alternating bands of light and darkness. The bright regions are stellar nurseries, places where new stars are being born, where hydrogen gas heats to millions of degrees, where the blue and white glow of young stars ignites the surrounding clouds. The dark regions are lanes of interstellar dust, where light is absorbed, where matter waits patiently to be compressed into future generations of stars. But there is something more poetic than numbers. When you see Andromeda with the naked eye, you do not see detail. You see only a faint smudge, a ghostly glow, like something half-remembered from a dream. And perhaps that is its true beauty. Because within that blur lies an entire parallel universe, a world where countless forms of life may exist, where endless stories may be unfolding in a place we will never directly witness. Ancient Greek astronomers saw Andromeda and called it the Little Cloud. It was not until the year 1924 that the astronomer Edwin Hubble proved Andromeda was not a cloud of gas within our Milky Way, but a separate galaxy, an independent island universe far beyond the borders of our cosmic home. When Hubble observed Andromeda through the 100-inch Hooker telescope, the largest telescope in the world at the time, he discovered Cepheid variable stars. These stars brighten and dim in regular cycles, and those cycles are directly linked to their true brightness. By measuring the rhythm of their light, Hubble was able to calculate the distance to Andromeda, and he realized it lay at an almost unimaginable remove, more than 2 million light-years away. That discovery transformed humanity's understanding of the universe. Before then, we believed the Milky Way was everything that existed. Now we know there are billions of galaxies out there, and Andromeda is just one of them, though it is the largest and closest member of our local group of galaxies. But let us return to the personal experience. When you see Andromeda with your naked eye, you are witnessing something extraordinary. The light reaching you has been traveling for 2.5 million years. Every photon, every tiny packet of light, left a star in Andromeda at a time when our species did not yet exist as Homo sapiens. And now, that photon strikes your retina, activates rods and cones, sends electrical signals to your brain, and becomes an image, faint, but undeniably real. You are looking into the past. Every time you gaze at the night sky, you become an archaeologist of time. The nearest stars, only a few light years away, show you the universe as it was a few years ago. More distant stars, hundreds of light years away, reveal the past as it was in the Middle Ages. But Andromeda, at 2.5 million light years, shows you a time when woolly mammoths still roamed the Earth. That is why observing Andromeda is not only science, it is philosophy. It reminds us that time is not a simple flow. It is something stranger, more intricate. In the universe, the past and the present coexist. Andromeda today, with all its stars, planets, and perhaps even life, exists somewhere out there right now. But we cannot see it. We can only see its version from 2.5 million years ago. That leads to a profound question. If we can never see Andromeda's present, what does the present even mean? Is now merely an illusion, a concept our brains invent to make sense of reality? In the universe, everything is either past or future, but never truly now. Take a deep breath once more. Feel that wonder. You and Andromeda exist in different moments in time, yet you are connected by light, an invisible thread stretched across space and time. And now, having seen what Andromeda is like, having felt its faint yet majestic presence in the sky, a new question emerges. How did such a colossal galaxy come to be? Where did more than 1 trillion stars come from? What is the origin of Andromeda, and what might it tell us about the origin of ourselves? Let's rewind time. Not 2.5 million years, but 13.8 billion years, back to a moment when the universe was nothing more than a singular point, so hot that no atoms could exist, only pure energy. This was the Big Bang, the Great Bang, although it was not an explosion in the usual sense. It was the expansion of space itself, a sudden and violent stretching of the fabric of the cosmos. In the first few minutes after the Big Bang, the universe cooled enough for protons and neutrons to combine into the first atomic nuclei, mostly hydrogen and helium. But there were still no stars. No galaxies. Just a vast, hot, nearly uniform sea of gas filling all of space. It took another 380,000 years for the universe to cool enough for light to travel freely. This was the moment when the cosmic microwave background, known as the CMB, was created, a faint afterglow that we can still detect today with satellites like Planck. This radiation gives us a snapshot of the early universe, almost perfectly smooth, but with tiny fluctuations, slight ripples in density, places with a little more matter, places with a little less. Those tiny ripples became the seeds of everything we see today. Gravity, a weak but relentless force, began pulling matter toward the slightly denser regions. Over time, those regions attracted more and more material, and gradually, after hundreds of millions of years, enormous clouds of gas collapsed in on themselves, giving birth to the first stars. This was the cosmic dawn. These first stars were nothing like the ones we see today. They were massive, extremely hot, and short-lived, surviving only a few million years before exploding as supernovae, blasting the first heavy elements into space: carbon, oxygen, iron, the ingredients necessary for life. But Andromeda did not appear right away. Its story is far longer and far more complex. According to simulations by astrophysicists, Andromeda began forming around 10 billion years ago, about 3.8 billion years after the Big Bang. By then, the universe had matured. Multiple generations of stars had already lived and died, and space had been enriched with heavy elements. Andromeda did not form from a single cloud of gas. Instead, it was built through a series of collisions and mergers with smaller galaxies. This is how most large galaxies come to be, not through a quiet birth, but through cosmic battles, chaos, and impact. Using data from the Gaia satellite and the Hubble Space Telescope, scientists have discovered that Andromeda has cannibalized many smaller satellite galaxies in its past. They found stellar streams, long ribbons of stars stretched around Andromeda like brushstrokes on a painting. These are the remains of smaller galaxies that were torn apart and absorbed into Andromeda's massive body. Imagine a slow dance lasting billions of years. A small galaxy, perhaps containing only a few billion stars, orbits Andromeda. Andromeda's gravity pulls more strongly on the stars closer to it than on those farther away. This difference, known as tidal force, begins to stretch the smaller galaxy, pulling it into a long stream. Over millions of years, the galaxy loses its shape, its stars scattered, until it is completely absorbed by Andromeda. But those stars do not vanish. They are still there, now part of Andromeda, carrying with them the story of their distant origins. By studying their motions and chemical compositions, astronomers can reconstruct Andromeda's history, much like archaeologists reading layers of rock to understand Earth's past. One of the most important discoveries came when scientists mapped Andromeda's outer regions in detail and found at least 13 intact satellite galaxies still orbiting it, small galaxies that have not yet been fully absorbed. They also found evidence for at least 2 major collisions in Andromeda's past. The first happened about 8 billion years ago, when a galaxy with roughly 20% of Andromeda's mass slammed into it. This collision likely triggered an intense burst of star formation and may have helped shape the spiral structure we see today. The second collision, more recent, occurred about 2 billion years ago with a galaxy known as M32P. That galaxy was torn apart, and scientists believe that the satellite galaxy M32 we see today is what remains, the dense core of M32P. This event may have created the enormous ring of gas observed in Andromeda's disk. But behind the numbers and the data lies a deeper philosophical story. Andromeda, like us, like everything in the universe, is not a fixed object. It is a flow, a continuous process of change. The stars we see in Andromeda today are not its original stars. Many have died and been replaced by new generations. Its structure has evolved over billions of years and will continue to evolve. In Buddhism, there is a concept called impermanence, the idea that everything changes and nothing exists forever in a fixed form. Andromeda is a perfect example of this. It was once many smaller galaxies. Now it is one great galaxy. And in the future, it will merge with the Milky Way to become something entirely new. This also reminds us that we ourselves, our bodies, our minds, our awareness, are the result of a similar long process. The atoms in your body were not created on Earth. They were forged inside stars through nuclear fusion. When those stars died, they scattered those atoms into space. Those atoms drifted through the universe for billions of years before coming together to form the Sun, the Earth, and eventually, you. Carl Sagan once said that we are made of star stuff. And he was right. Every carbon atom in your body was created inside a star, perhaps billions of years ago, perhaps in a distant galaxy. Every oxygen atom you breathe, every calcium atom in your bones, every iron atom in your blood is a legacy of stars that lived and died long before you were born. So when you look at Andromeda and wonder about its origins, you are also asking about your own. The story of Andromeda is our story. We all come from the same source, from the same great beginning 13.8 billion years ago. We are siblings of the stars, of the galaxies, of everything in the universe. And now, having traced Andromeda's origins, a new question emerges. In a galaxy that vast, with more than 1 trillion stars, could there be other life out there? Is someone, somewhere in Andromeda, looking back toward the Milky Way and wondering if they are alone? Imagine standing on a distant planet, orbiting some star in the Andromeda galaxy. That planet's sky might hold 2 suns, or even 3, because many stars in Andromeda exist in pairs or small groups. You look up at the night sky, if that planet even has a night, and you notice a faint, hazy streak of light far away. That is the Milky Way, our home, sitting 2.5 million light-years from where you stand. And perhaps, at that very moment, a creature on that planet is asking the same quiet question, is anyone out there? This is one of the deepest questions science and philosophy have ever asked. Are we alone in the universe? And if the answer is no, then where might life exist? In the Milky Way? In Andromeda? Or in galaxies even farther away? To begin answering this, we need to understand what life requires. Based on life on Earth, the only example we truly know, life needs a few basic ingredients: liquid water, chemical elements like carbon, hydrogen, nitrogen, oxygen, and phosphorus, and a stable source of energy. These conditions are not rare in the universe. In fact, they appear to be quite common. In the Milky Way, scientists estimate that there are around 40 billion Earth-sized planets located in the so-called habitable zone, where temperatures allow liquid water to exist. This estimate comes from data collected by NASA's Kepler mission, a space telescope that spent years searching for planets beyond our solar system. If the Milky Way contains 40 billion potentially habitable planets, and Andromeda is even larger, with more stars than our galaxy, then it is reasonable to think that Andromeda might host 100 billion, or even 200 billion planets capable of supporting life. These numbers are not science fiction, they are calculations grounded in probability and real observations. But having planets does not guarantee life. Life, at least as we understand it, is rare and fragile. It requires not only the right physical conditions, but also a long chain of fortunate events, the formation of complex organic molecules, the emergence of cell membranes, the rise of genetic codes like DNA or RNA, and the ability to replicate. On Earth, life appeared very early in the planet's history, only about 700 million to 1 billion years after Earth formed. This suggests that when conditions are right, life can emerge relatively quickly. But complex life, animals, plants, multicellular organisms, took billions of years more to develop. And intelligent life, humans, has existed for only a few million years. This leads to a paradox. If simple life like bacteria and single-celled organisms forms easily, then the universe could be filled with it. But complex and intelligent life may be extraordinarily rare. This idea lies at the heart of the Fermi paradox. If extraterrestrial life is common, why have we not seen any sign of it? There are many possible explanations. Intelligent civilizations may tend to destroy themselves through nuclear war, environmental collapse, or uncontrolled technology. The distances between civilizations may simply be too vast for communication. Or perhaps, the most unsettling possibility of all, we really are alone, or almost alone, in a universe so large it is hard to comprehend. Andromeda adds another layer to this perspective. If intelligent life exists there, could we ever detect it? The answer is probably no, at least not with current technology. A distance of 2.5 million light-years is enormous. Even if a highly advanced civilization in Andromeda were broadcasting the strongest radio signals it could produce, those signals would take 2.5 million years to reach us, and by then they would be so faint as to be nearly undetectable. Even more strangely, if they sent a message today, we would not receive it for 2.5 million years. And if we replied, our response would take another 2.5 million years to get back to them. A simple exchange of one question and one answer would take 5 million years, longer than our species has existed on Earth. But perhaps the search is not really about finding anyone. Perhaps it is about the question itself. Astronomer Carl Sagan once wrote, "The universe is a pretty big place. If it's just us, it seems like an awful waste of space." That idea, that the universe is too vast to contain only one civilization, continues to motivate scientists to keep looking. The SETI project has spent decades listening for signals from stars in the Milky Way. So far, nothing convincing has appeared, but the search continues. Now, with the James Webb Space Telescope, we can analyze the atmospheres of distant exoplanets, searching for possible signs of life, gases like oxygen, methane, or other chemical fingerprints that living organisms might produce. If we were to find evidence of life, even something as simple as bacteria, on another planet, it would be one of the most important discoveries in human history. It would show that life is not a lucky accident that happened only once on Earth, but a natural feature of the universe, something that can arise wherever conditions allow. And if simple life is common, then there is reason to hope that complex life, and perhaps even intelligent life, exists somewhere as well. Maybe not in our Milky Way. But maybe in Andromeda. Or in galaxies far beyond that. There is an idea in quantum biology called quantum coherence, the suggestion that biological systems may use quantum effects to perform functions like photosynthesis or navigation. If this is true, it hints that life is not just chemistry, but something tied to the deepest laws of the universe itself. If so, then life may be an inevitable part of the cosmos, a way for the universe to become aware of itself. We, and perhaps beings in Andromeda too, are not outsiders looking in. We are pieces of the universe that have learned to think, to reflect, and to ask questions. It is a beautiful and profound thought. When you look at Andromeda and wonder whether life exists there, you are not just searching for aliens. You are searching for other awakened parts of the universe, parts that can love, fear, hope, and dream, just like we do. And whether or not we ever find them, the search still matters. Because it reminds us that we are part of something far greater than ourselves. We are not isolated islands, but waves in the same ocean, notes in the same cosmic symphony. But if life, and perhaps intelligent life, does exist in Andromeda, it must face the same challenges we do. It must exist in a universe where time moves forward, where everything changes, where even stars are born and die. And that leads us to the next question. How does time flow in Andromeda? And is there any way to escape the limits that time places on us? Take one more deep breath. Feel this moment, the instant you are hearing these words, the rhythm of your heartbeat, the air moving in and out of your lungs. This is your present. But here is the strange part. The present of someone standing on a planet in Andromeda might not be the same as yours. And I am not just talking about differences caused by distance, but something far deeper, the very nature of time itself. In classical physics, the physics of Newton, time was considered absolute. It flowed steadily, like a river whose speed never changes, no matter where you are in the universe. 1 second on Earth was 1 second in Andromeda, and 1 second everywhere else. Time was something outside of us, independent of space and matter. Then Einstein arrived, and everything changed. In 1905, Einstein published the theory of special relativity. He showed that time is not absolute. It depends on the motion of the observer. If two people move at different speeds, time flows differently for each of them. This is not an illusion, but a real, physical effect that has been confirmed thousands of times by experiments. For example, if you were traveling on a spaceship moving at nearly the speed of light, time for you would pass more slowly than for someone who stayed on Earth. This is called time dilation. 1 hour on the spaceship could correspond to many years on Earth. You could leave Earth, travel for what feels like a few years to you, then return to find that decades, or even centuries, have passed. But there is another kind of time dilation, one connected to gravity. This comes from general relativity, which Einstein published in 1915. According to this theory, mass and energy curve spacetime. And when spacetime curves, time itself flows differently. Near a very massive object, like a star or a black hole, time passes more slowly than it does farther away, where gravity is weaker. This effect has been confirmed using extremely precise atomic clocks. If you place one clock on the ground and another on the top of a mountain, the clock on the mountain, slightly farther from Earth, where gravity is slightly weaker, will tick faster than the one on the ground. The difference is incredibly small, only a few billionths of a second per day, but it is real and measurable. So how does time flow in Andromeda? The answer depends on where you are within the galaxy. If you are far from the galactic center, where matter is spread thinly, time flows relatively faster. But if you move closer to the heart of Andromeda, where a supermassive black hole sits with a mass 100 million times that of the Sun, time flows significantly more slowly. Imagine you have a friend flying near the central black hole of Andromeda while you remain farther away. If your friend is close enough, 1 hour for them could equal many years for you. They would age more slowly. Their heart would beat more slowly. Every biological process in their body would run at a slower pace. Yet from their perspective, everything would feel completely normal. They would not sense any difference at all. Only when they returned and compared themselves to you would they realize that you had aged far more than they had. This is not science fiction. This is proven physics. GPS satellites orbiting Earth must constantly adjust their clocks to account for both effects, time dilation due to motion and time dilation due to gravity. Without these corrections, GPS would drift by kilometers in just a few hours. But there is a deeper philosophical layer here. If time is not absolute, if it flows differently for different observers, then what does the present really mean? Is there a single shared now for the entire universe, or does each person, each planet, each galaxy have its own now? According to Einstein, there is no universal now. The idea of a single present moment shared by the entire universe is an illusion. What we call now only has meaning locally, within a small region of spacetime around us. In distant places, with different gravitational fields and different motions, the now can be completely different. This means that the present of a being in Andromeda, if such beings exist, may not be synchronized with our present. Not because of distance, but because of the nature of time itself. And this leads to one of the strangest ideas in modern physics: the past and the future may exist at the same time, depending on your point of view. Some physicists, like Julian Barber, have proposed an even more radical idea, that time may not exist at all. According to him, what we experience as time is just a sequence of static states, individual presents, and our brains create the illusion of flow by comparing these states to one another. The universe does not move through time. Instead, every moment, past, present, and future, exists simultaneously, and our consciousness simply experiences them in a particular order. This is a difficult idea to grasp, but it has a strange kind of beauty. If all moments exist at once, then nothing is ever truly lost. Every moment of your life, your childhood, your adulthood, your old age, exists forever somewhere in the fabric of spacetime. The past does not disappear. It is still there, we just cannot access it from our present. In Buddhism, there is a concept called timelessness, stepping beyond time and living fully in the present moment, without being dragged by the past or pulled by the future. Perhaps this is not only a spiritual practice, but also a deep insight into the nature of reality. Because if time is an illusion, then the only way to truly live is to live in the now, not now as a point on a timeline, but now as the entirety of existence. But let us return to Andromeda. If time flows differently in different regions of the galaxy, what does this mean for life? If a civilization lived near the central black hole, they would age more slowly than a civilization living on the galactic outskirts. Their history would unfold at a different pace. What feels like a century to them could be a millennium to others. And if they had the technology to travel between regions of different gravity, they could use time dilation to travel into the future. By going near a black hole, staying there for a while, then returning, they could leap forward in time, not by moving faster than light, but by allowing time elsewhere to flow faster than it does for them. This opens up possibilities that are both wondrous and terrifying. Wondrous because it means that time travel, at least travel into the future, is theoretically possible. Terrifying because it means that if we ever leave Earth to explore Andromeda or places even farther away, we may never truly come home. By the time we return, that home may no longer exist. The people we love may have grown old and passed away. Entire civilizations may have changed beyond recognition. This is one of the deepest sorrows hidden within relativity. The farther we go, the faster we move, the more alien we become to the time of those we leave behind. Time does not only separate us by distance, but by the very rate at which it flows. And yet, perhaps this is also a reminder to cherish the present moment. Because now, this moment, as you are hearing these words, is all we ever truly have. The past is gone. The future has not arrived. And between them lies an incredibly brief moment we call the present. That is where we live. That is where we love. That is where we exist. And when we look toward Andromeda, when we reflect on time and space, perhaps what we are really searching for is not answers about distant galaxies, but understanding of ourselves, of how we experience time, of why we fear loss, of our longing for eternity. But if time in Andromeda can flow differently, if the universe has no single shared now, then what will the future be like? Andromeda and the Milky Way are rushing toward each other. One day, they will collide. And when that happens, time, and the universe itself, will change in ways we are only just beginning to understand. Close your eyes. Imagine yourself floating in space, far beyond every galaxy, at a place where you can see both Andromeda and the Milky Way at the same time. Two enormous glowing disks, each holding hundreds of billions of stars, slowly spinning in the cosmic dark. If you could fast forward time, you would notice something strange. These two galaxies are moving closer together. Not because they want to, but because gravity, gentle yet relentless, is pulling them into an unavoidable dance. Right now, Andromeda is rushing toward the Milky Way at about 110 kilometers per second, roughly 400,000 kilometers per hour. That sounds terrifying, but compared to the distance between them, about 2.5 million light-years, it is an almost leisurely drift. According to calculations from NASA and astronomers around the world, Andromeda will not collide with the Milky Way for another 4.5 billion years. 4.5 billion years, a span of time that is nearly impossible to grasp. To put it into perspective, Earth itself formed about 4.5 billion years ago. So the wait until Andromeda and the Milky Way collide is as long as the entire history of our planet, from a molten ball of rock, through the emergence of the first life, through mass extinctions, through the rise and fall of dinosaurs, the evolution of mammals, and finally, the appearance of humans. But let us fast forward to that distant moment. You are standing on Earth, assuming the planet still exists, on a night 4.5 billion years in the future. You look up at the sky, and what you see is nothing like today. Andromeda is no longer a faint smudge. It is huge. Enormous. It fills more than half the sky, a vast disk packed with billions of sparkling stars, its spiral arms stretching like waves of light. This is the early stage of the collision. The two galaxies are now so close that you can see Andromeda's details with the naked eye. Bright clouds of gas, glowing star-forming regions, dark lanes of dust. And around Andromeda, you can also see its smaller satellite galaxies, companions orbiting it like tiny moons. But the word collision is misleading. When galaxies collide, stars do not slam into each other. The distances between stars, even in crowded galaxies, are immense. The nearest star to the Sun is about 4.2 light-years away. If you shrank the Sun down to the size of a golf ball, the closest star, Proxima Centauri, would be another golf ball sitting about 1,300 kilometers away. So when Andromeda and the Milky Way collide, the stars will mostly pass right by one another, like two clouds of dust drifting through each other. The chance of two stars actually crashing together is almost zero. What does happen is far more subtle and far more dramatic. The gravitational fields of the two galaxies interact, tugging and pushing stars onto new, chaotic paths. Computer simulations from NASA show that this will not be a single encounter. The galaxies will pass through each other, then gravity will pull them back together, and they will pass through again. This process will repeat over billions of years. With each pass, the galaxies lose orbital energy, until finally, about 7 billion years after the first encounter, they fully merge into a single new galaxy. This new galaxy will no longer be a spiral. The collision will destroy the delicate spiral structures of both galaxies. Instead, the result will be an elliptical galaxy, an oval-shaped system common among large, old galaxies. Astronomers have already given it a friendly name, Milkomeda, a blend of Milky Way and Andromeda. But what about Earth? What about the Sun? What about us, if humans or anything descended from us still exist by then? The good news is that the chance of the Sun directly colliding with another star remains extremely small, about 1 in a million. Even as the galaxies pass through each other, most stars will simply move through the vast empty spaces between other stars. The bad news is that the Sun may be knocked out of its current position. Andromeda's gravity could alter the Sun's orbit, pushing it farther from the galactic center, or even ejecting it entirely from the newly formed galaxy. If that happens, Earth, assuming it still orbits the Sun, would drift through intergalactic space, a dark and lonely place between galaxies. But there is even worse news. Long before Andromeda and the Milky Way collide, the Sun itself will undergo dramatic changes. The Sun is a main sequence star, generating energy by fusing hydrogen in its core. But that fuel is not infinite. In about 5 billion years, roughly 500 million years before the first close encounter between Andromeda and the Milky Way, the Sun will run out of hydrogen in its core. When that happens, the Sun will begin burning hydrogen in shells around the core. This will cause it to expand, transforming into a red giant. It will grow so large that it will swallow Mercury, Venus, and possibly Earth. Temperatures on Earth will rise until the oceans boil, the atmosphere escapes into space, and life, at least as we know it, becomes impossible. So when Andromeda and the Milky Way finally collide, Earth, if it still exists at all, will be a scorched, airless rock, with no water and no life. Unless humans, or our descendants, have found a way to migrate to another star system, another planet, another home. That is one reason why space exploration is not just curiosity, but survival. If we want humanity, or any life born on Earth, to endure for the long term, we must learn to live beyond this planet. We must become a multi-planetary species, and eventually, a multi-galactic one. Yet even if we never manage that, the collision between Andromeda and the Milky Way is still beautiful in its own way. It will trigger a massive wave of star formation. As clouds of gas from the two galaxies crash into each other, they will be compressed, and that compression will cause the gas to collapse, forming millions, perhaps billions, of new stars. The sky, if anyone is left to see it, will blaze with the light of newborn stars. Young, hot, blue and white stars will illuminate the surrounding gas clouds, creating brilliant nebulae. It will be an era of rebirth and creation, rising out of cosmic chaos. At the center of the new galaxy, two supermassive black holes, one from the Milky Way and one from Andromeda, will slowly spiral together and merge. This process will generate gravitational waves, ripples in spacetime so powerful they could be detected from galaxies billions of light-years away. It will be one of the most energetic events in the universe, a deep cosmic shout echoing through the fabric of spacetime. There is also a philosophical beauty in all of this. The collision between Andromeda and the Milky Way is not an ending. It is a transformation. Like a caterpillar becoming a butterfly, two galaxies will become something new, different, yet still carrying the essence of both. It is a reminder that in the universe, nothing remains fixed forever. Everything changes. Stars are born and die. Planets form and are destroyed. Galaxies collide and merge. And even we, with our fleeting bodies, are part of that vast flow. Perhaps what matters most is not existing forever, but existing with meaning. In the brief time we have, whether 80 years, 100 years, or even billions of years, if humanity learns to endure, we can love, create, explore, and leave our mark on the universe. And when Andromeda and the Milky Way finally merge into Milkomeda, perhaps somewhere in that new galaxy, there will be beings who look up at the sky and wonder about the past, about the two galaxies that once existed before becoming their home. And perhaps they will tell stories about us, about creatures who lived on a small planet, orbiting an ordinary star, in one of two ancient galaxies. But before any of that happens, before Andromeda and the Milky Way collide, there is another question to answer. How do we know all of this? How can scientists look into the past and predict the future of galaxies? Let us return to a dark night, before electricity, before telescopes, when humans had only their eyes and their curiosity. They looked up at the sky and saw the stars, the constellations, and sometimes, if their eyes were sharp enough and the sky was dark enough, a faint smudge in the constellation of Andromeda. They did not know what it was. A cloud? smoke from the gods? Or simply a flaw in the heavens? It took thousands of years for us to understand that this faint blur was a galaxy, an island universe containing more than 1 trillion stars. And the journey to that understanding is not just a story of technology, it is a story of imagination, perseverance, and the unrelenting human desire to understand our place in the cosmos. The Persian astronomer Abd al-Rahman al-Sufi was among the first to record Andromeda in the year 964. In his book, The Book of Fixed Stars, he described it as a small cloud. To him, it was simply a strange phenomenon, a question mark written into the sky. The true exploration began with the invention of the telescope. In the year 1610, Galileo pointed his crude telescope toward the heavens and saw things no one had ever seen before: mountains on the moon, moons orbiting Jupiter, the phases of Venus. He opened a new door, not only technologically, but philosophically. The universe was no longer a perfect, unchanging sphere. It was a place of motion, of structure, of other worlds. Over the centuries, telescopes grew larger and more powerful. In the year 1845, William Parsons, the 3rd Earl of Rosse, built a giant telescope with a mirror 1.8 meters across. With it, he sketched detailed drawings of Andromeda and other so-called spiral nebulae. He could see their spiral structure, but he still did not know what they were. Were they clouds of gas forming new star systems inside the Milky Way? Or were they entirely separate galaxies? This question ignited what became known as the Great Debate, which lasted into the early 20th century. On one side, led by Harlow Shapley, were those who believed the Milky Way was the entire universe, and that spiral nebulae like Andromeda were gas clouds within it. On the other side, led by Heber Curtis, were those who believed these nebulae were island universes, separate galaxies far beyond the Milky Way. The debate was settled in the year 1924 by Edwin Hubble, the man whose name now graces the most famous space telescope in history. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble discovered Cepheid variable stars in Andromeda. These stars pulse in brightness, and the astronomer Henrietta Swan Leavitt had shown that the period of this pulsing is directly related to their true brightness. By measuring the periods of the Cepheids in Andromeda, Hubble could calculate how bright they really were. And by comparing that true brightness to how bright they appeared from Earth, he could determine their distance. The result was astonishing. Andromeda lay more than 2 million light-years away, far beyond any distance ever measured before. In that moment, the universe suddenly became much larger. We realized that the Milky Way was just one of billions of galaxies. We were not at the center of the universe. Our galaxy was not even special. We were a tiny speck in a vast cosmic ocean. But Hubble did not stop there. He continued studying other galaxies and discovered something even more surprising. Nearly all of them were moving away from us, and the farther away they were, the faster they were receding. This was the evidence that the universe itself is expanding, a discovery that would eventually lead to the Big Bang Theory. And yet, Andromeda was different. It was not moving away. It was moving toward us. Its light was shifted toward the blue end of the spectrum, not red like most other galaxies. This meant that Andromeda was rushing toward us at a speed of about 110 kilometers per second. This discovery raised a new question. Why was Andromeda coming toward us while most other galaxies were flying away? The answer lies in gravity. Even though the universe is expanding, galaxies that belong to the same group, like the local group that includes the Milky Way and Andromeda, are bound together by gravity. On these local scales, gravity is stronger than cosmic expansion, allowing galaxies to move toward one another. After Hubble, technology continued to advance. Ground-based telescopes grew ever larger and more precise. But the real leap came in the year 1990, with the launch of the Hubble Space Telescope. Placed above Earth's atmosphere, Hubble could observe the universe without atmospheric distortion, producing images sharper and more detailed than anything seen before. Hubble captured stunning images of Andromeda, revealing its spiral arms, its star-forming regions, and billions of individual stars. In the year 2015, a team of astronomers released a massive mosaic built from 7,398 individual images, containing more than 1.5 billion pixels and showing over 100 million stars in Andromeda. It was the most detailed image of a galaxy ever taken. But we do not study Andromeda using visible light alone. We observe it across the electromagnetic spectrum, in radio waves, infrared light, X-rays, and gamma rays. Each wavelength reveals a different side of the galaxy. Radio waves allow us to see cold clouds of hydrogen gas, the raw material for new stars. Infrared light reveals warm dust and hidden star-forming regions. X-rays expose the hottest and most energetic objects, such as black holes and neutron stars. In the year 2003, the Spitzer Space Telescope, which observed an infrared light, imaged Andromeda and revealed a hidden structure, a vast ring of gas and dust encircling the galaxy's center. This ring, about 75,000 light-years across, was formed by a collision with a smaller galaxy roughly 2 billion years ago. Then, in the year 2021, the James Webb Space Telescope was launched. It is the most powerful telescope ever built, with a primary mirror 6.5 meters wide and extraordinary sensitivity in the infrared. James Webb can see the first stars in the universe, the most distant galaxies, and even analyze the atmospheres of planets orbiting other stars. James Webb has begun observing Andromeda, and the early images are breathtaking. They reveal star-forming regions in unprecedented detail, individual stars millions of light-years away, and the intricate structure of gas and dust clouds. These observations are helping us understand how stars form, how galaxies evolve, and how the universe changes over time. But there is a deeper question beneath all of this. Why do we do it? Why do we invest billions of dollars to build telescopes to study a galaxy 2.5 million light-years away, a place we will never visit, at least not anytime soon? The answer has many layers. On the surface, it is about scientific knowledge. By studying Andromeda, we learn how galaxies form and evolve. We learn about gravity, black holes, and star formation. This knowledge does more than satisfy curiosity, it finds practical applications, from GPS technology to nuclear energy. But at a deeper level, studying Andromeda is about understanding ourselves. When we look at Andromeda, we are looking into a mirror. We see our past, what the Milky Way may have looked like billions of years ago. We see our future, as Andromeda and the Milky Way will one day merge. And we see our place in the universe, not central, not special, yet still part of something vast and beautiful. Carl Sagan once wrote about the pale blue dot, the photograph of Earth taken by Voyager 1 from 6 billion kilometers away. In that image, Earth is a tiny speck, suspended in a beam of sunlight. Sagan wrote, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone who ever was, lived out their lives." When we look at Andromeda, we feel something similar, but on an even grander scale. We realize that not only Earth, but our entire Milky Way, with its 200 billion stars, is just a speck in the vastness of the cosmos. And that feeling of smallness, rather than leading to despair, can inspire humility and gratitude. And yet, one final question remains. If we can observe Andromeda from afar, is there any way to truly reach it? Could our technology, or that of future civilizations, ever cross a distance of 2.5 million light-years? Take a deep breath. Imagine yourself standing on the launch pad of a spacecraft. This is not an ordinary ship, not the kind NASA uses to send humans to the Moon or Mars. This vessel is built for a journey no one has ever taken, a voyage to Andromeda, 2.5 million light-years away. You step inside. The hatch seals behind you. The engines begin to hum. And then you leave Earth, leave the Sun, leave everything you have ever known. Your destination is a distant galaxy. The only question is, how long will it take? Here is the problem. With today's technology, we cannot reach Andromeda. Not because we lack intelligence, but because the laws of physics impose limits that are nearly impossible to overcome. The fastest human-made object ever created is the Parker Solar Probe, a spacecraft launched by NASA in 2018 to study the Sun. At its top speed, it travels at about 700,000 kilometers per hour, roughly 0.064% of the speed of light. That sounds fast, but at that speed, a trip to Andromeda would take around 4 billion years, nearly the age of Earth itself. So we would need to travel faster, much faster. Ideally, close to the speed of light, about 300,000 kilometers per second. But this is where Einstein's theory of relativity begins to cause trouble. According to Einstein, nothing, no matter, no information, can move faster than the speed of light. This is not a technological limit, it is a fundamental limit of the universe. And as you approach the speed of light, reality starts to behave in very strange ways. First, your mass increases. The faster you move, the heavier you become, and the more energy you need to keep accelerating. As you approach the speed of light, your mass approaches infinity, and so does the required energy. In practical terms, there is not enough energy in the universe to push an object with mass all the way to the speed of light. Second, time slows down. This is the time dilation effect we mentioned earlier. If you travel at 99% of the speed of light, time for you slows by a factor of about 7 compared to someone on Earth. 1 year aboard your spacecraft would equal 7 years back home. And if you could reach 99.999% of the speed of light, the effect becomes far more extreme. Only a few decades might pass for you, while millions of years pass on Earth. You could reach Andromeda within your lifetime, but when you arrive, the Earth you left behind would be gone. Everyone you ever loved would be long dead. The civilization you knew may have collapsed and been replaced by something entirely different. This is the loneliness of intergalactic travel. You may reach your destination, but you can never truly go home, at least not to the same home you left behind. But let us imagine we could accept that. Imagine we found a way to generate enough energy to push a spacecraft close to the speed of light. Are there any theoretical ideas that could make this possible? One proposal is the use of light sails. This would be a massive, ultra-thin, reflective sail. A powerful laser, fired from Earth or from orbit, would shine onto the sail, and the pressure of the light itself would push the spacecraft forward. No fuel. No engines. Just light. The Breakthrough Starshot project, funded by billionaire Yuri Milner and supported by Stephen Hawking, is exploring this idea. The goal is to build tiny spacecraft, weighing only a few grams, equipped with light sails, and use a powerful laser array to accelerate them to about 20% of the speed of light. At that speed, a probe could reach Proxima Centauri, the nearest star, in roughly 20 years. But Andromeda is far farther away. Even at 20% of the speed of light, the journey would still take about 12.5 million years. And that assumes you could maintain that speed for the entire trip, which is far from simple. At such velocities, even tiny grains of interstellar dust or small debris could destroy a spacecraft upon impact. So is there any other way? A few ideas, often labeled as science fiction but rooted in real physics, have been proposed. One of them is the warp drive. First proposed by physicist Miguel Alcubierre in 1994, this concept does not violate the speed of light limit because it does not move the spacecraft through space. Instead, it contracts space in front of the ship and expands space behind it, creating a warp bubble. Inside this bubble, the spacecraft itself remains stationary relative to its local space. It sounds like magic, but Einstein's general theory of relativity allows space-time to bend, contract, and expand. The problem is that a warp drive would require a form of exotic energy known as negative energy. We do not know whether this kind of energy exists in usable amounts. Some quantum effects, like the Casimir effect, suggest that negative energy can exist on extremely small scales, but producing enough of it to move a spacecraft is an entirely different challenge. Another idea involves wormholes. These would be shortcuts through space-time, connecting two distant points. If you could create a wormhole with one end in the Milky Way and the other in Andromeda, you could step through and arrive almost instantly, or at least very quickly. But once again, there are serious problems. We do not know whether wormholes can exist naturally, or whether they can be created at all. Even if they do exist, they may be violently unstable and collapse the moment you try to pass through them. And to keep a wormhole open, you would again need negative energy, the same obstacle faced by warp drives. So the outlook seems bleak. Based on what we know today, traveling to Andromeda appears impossible, at least not within our lifetimes, and perhaps not within thousands of future generations. But maybe that is the wrong way to think about it. Maybe instead of sending biological humans to Andromeda, we could send something else. One possibility is artificial intelligence. A machine does not need air, food, or water. It could survive in space for thousands, even millions of years, as long as it has a power source and the ability to repair itself. An AI could be programmed to explore Andromeda, collect data, and send information back to Earth. Or perhaps we could send our consciousness itself. If, someday, we learn how to upload the human mind into a computer, a digital copy of you could be transmitted to Andromeda as a radio signal. That signal would travel at the speed of light, taking 2.5 million years to arrive. But once it did, it could be downloaded into a robotic body or a virtual environment, and you, or at least a version of you, would exist there. These ideas sound like science fiction, and for now, they are. But only a century ago, the idea of sending humans to the moon was also considered science fiction. And today, we have done it 6 times. Yet there is a deeper philosophical question. Should we go to Andromeda, even if we can? The universe is vast, and the distances between galaxies may exist for a reason. Perhaps they serve as a kind of safeguard, preventing civilizations from colliding before they are mature enough. If humans, with all our flaws, with our history of war, violence, and environmental destruction, gain the ability to travel between galaxies, would we carry those problems with us? Or perhaps, by the time we develop intergalactic travel, we will also have grown morally and spiritually. Maybe a civilization capable of crossing galaxies would be one that has moved beyond violence, one that has learned to live in balance with itself and with its environment. It is a hopeful thought. It suggests that the journey to Andromeda is not just about technology, but about the evolution of human consciousness. It is about becoming the best version of ourselves, not just as individuals, but as a species. Maybe that is the real reason we look toward Andromeda. Not because we want to conquer it, but because it reminds us of our own potential, of what we might become if we are patient enough, creative enough, and wise enough. But as we dream of these future journeys, another question remains. Within the Andromeda galaxy itself, what mysteries are still waiting to be uncovered? What is it that, even with our most advanced technology, we still do not understand? Let your shoulders relax. Let your breathing become light and steady. We have come a long way, from spotting Andromeda in the night sky, to tracing its origins, to wondering about life, to questioning the nature of time, and even dreaming of intergalactic travel. But now we arrive at what may be the most fascinating part of all, the things we do not know. Because science is not only about answers. It is also about questions. And Andromeda, despite more than a century of study, still holds mysteries that leave scientists puzzled, debating, and sometimes simply shrugging and saying, "We do not know." The first mystery, and perhaps the greatest, involves something we cannot see, dark matter. When astronomers measured how fast Andromeda rotates, they found something strange. The stars at the outer edges of the galaxy, far from the center, are moving much faster than expected based on the amount of visible matter. According to the laws of Newton and Einstein, orbital speed should depend on how much mass lies within that orbit. But the outer stars of Andromeda move as if there is far more mass present than we can actually see. This can mean only one thing. There is some kind of matter we cannot see or measure directly, yet it still exerts gravity. This is what we call dark matter. According to current calculations, about 85% of Andromeda's mass, and in fact the mass of most galaxies, is dark matter. Only 15% is ordinary matter, the stuff that makes stars, planets, and us. But what is dark matter? We do not know. It does not interact with light, it does not absorb it, reflect it, or emit it. It passes through everything like a ghost, leaving its presence known only through gravity. Physicists have proposed many candidates: weakly interacting particles, axions, primordial black holes. But so far, no experiment has detected it directly. This means that when you look at Andromeda, most of what makes up that galaxy is invisible to you. You are looking at an iceberg where only the tip is visible, a small fraction, while the vast majority lies hidden beneath the surface of reality. This is not just an academic problem. Dark matter shapes the structure of the universe. It is the scaffolding upon which galaxies are built. Without dark matter, galaxies would not have formed the way they did. Life, and we ourselves, might not exist at all. So when we look at Andromeda and ask about the nature of dark matter, we are really asking about the nature of the universe itself. We are asking about 85% of reality that we cannot see or touch, yet know is there. The second mystery concerns the supermassive black hole at Andromeda's center. We know it is there. We have measured its mass, somewhere between 100 million and 230 million times the mass of the Sun. We know it influences the motion of nearby stars. But we do not understand how it formed. How does a black hole grow that large? Black holes form from the collapse of massive stars, but those black holes weigh only a few dozen times the mass of the Sun. How do they grow into objects millions, or even billions, of times more massive? One idea is that they slowly feed on surrounding matter, gas, dust, stars, over billions of years. But calculations show this process is too slow to explain the supermassive black holes we see in young galaxies that formed only a few 100 million years after the Big Bang. Another idea is that supermassive black holes formed directly from the collapse of enormous gas clouds in the early universe, skipping the star stage entirely. Or perhaps they are the result of many smaller black holes colliding and merging. But we still do not know for sure. Which means that when we look toward the center of Andromeda, we are staring at one of the greatest mysteries in modern astrophysics, the origin of supermassive black holes. The third mystery involves Andromeda's history of collisions. We have already talked about how Andromeda has consumed many smaller galaxies in the past. But there is a deeper question. Did Andromeda ever collide with another galaxy of comparable size, a major collision that could completely reshape a galaxy? Astronomers have found evidence suggesting that Andromeda may have undergone a large collision about 2 billion years ago. They discovered a strange structure, a thick disk of old stars, that cannot be explained by normal galactic evolution. This structure may be the remnant of another galaxy that Andromeda absorbed. But the details remain unclear. How large was that galaxy? At what angle did it collide? And most importantly, did that collision trigger a wave of star formation, creating new stars and planets, and perhaps, just perhaps, creating conditions favorable for life? This is not only a question about Andromeda's past. It is also a question about our future. When Andromeda and the Milky Way collide, we want to know what will happen. And the best way to understand the future is to study the past, to see what has happened before. The fourth mystery involves stellar streams, long ribbons of stars stretching around Andromeda. These streams are the remains of satellite galaxies torn apart by Andromeda's gravity. But when scientists mapped them in detail, they noticed something odd. There are more streams than there are surviving satellite galaxies. This means more small galaxies were destroyed than we once thought. Even stranger, these streams are not randomly distributed. They tend to lie in a plane, orbiting Andromeda. This is difficult to explain, because if satellite galaxies arrived from all directions in three-dimensional space, we would expect their remnants to be spread out in 3 dimensions as well. So why are they confined to a plane? One hypothesis is that these satellite galaxies did not arrive randomly, but formed together from a larger structure, a cosmic flow of gas and dark matter. But this idea conflicts with standard models of galaxy formation. This is one of the great challenges of modern astrophysics. Observations do not always match theory. And when that happens, we face a choice: either revise the theory or seek better observations to understand what is really going on. The fifth mystery concerns the rate of star formation in Andromeda. When astronomers measure how quickly new stars are forming, they find that Andromeda is forming stars much more slowly than expected. The galaxy contains plenty of gas, the raw material for making stars, yet star formation is sluggish. Why? One possibility is that some mechanism is preventing the gas from collapsing into stars. It could be magnetic fields, pressure from existing stars, or energy from the central black hole. But we are not certain. And this matters because it shapes Andromeda's future. If star formation remains slow, Andromeda will gradually age, with more old stars and fewer young ones. Eventually, after tens of billions of years, all stars will die, and Andromeda will become a dark, cold, lifeless galaxy. But perhaps the collision with the Milky Way will change that. The collision could compress gas, trigger an intense burst of star formation, and give Andromeda, and the Milky Way, a kind of second youth. And finally, there is a deeper, more philosophical mystery. Is there something about Andromeda that we can never know? This is not a question of technology or time. It is a question about the nature of knowledge itself. There may be fundamental limits, barriers that no technology, no matter how advanced, can ever cross. For example, we will never be able to see inside the event horizon of Andromeda's central black hole. Anything that happens there, any secret it holds, will remain forever hidden from us. There are also limits set by time. Light from Andromeda takes 2.5 million years to reach us. This means we can never know what is happening there right now. We can only know its past, a past from 2.5 million years ago. And there may be limits to human consciousness itself. There may be aspects of the universe, extra dimensions, physical laws, forms of existence, that our brains are simply not designed to understand. Just as an ant cannot grasp Shakespeare, there may be aspects of Andromeda, and of the universe, that we can never fully comprehend. But this is not a reason to give up. On the contrary, this is the beauty of science. Science does not promise that we will know everything. It only promises that we will keep searching, keep asking questions, and keep pushing the boundaries of understanding a little farther. Along the way, in the search for answers, we learn not only about Andromeda, but about ourselves. We learn humility, curiosity, perseverance. We learn that not knowing is not a failure, but an invitation to explore. So when we look at Andromeda and see all its unresolved mysteries, we should not feel discouraged. We should feel excited. Because every mystery is an opportunity. Every unanswered question is a door waiting to be opened. And perhaps, in the future, when our descendants look up at the sky and see Andromeda larger and closer, they will have tools, ideas, and questions we have never imagined. And they will continue the journey we have begun. Take a slow breath out. Feel the weight of your body, the way it rests against the ground or the chair beneath you. You are here, on Earth, in this moment. And yet, in your mind, throughout this journey we have taken together, you have traveled through space and time. You have looked at Andromeda, a galaxy 2.5 million light-years away, and through it, you have looked into the universe itself. So what does Andromeda teach us? Not just about science, physics, numbers, or equations, but about something deeper, about our place in the cosmos, about the nature of existence, about how we might choose to live. The first lesson Andromeda teaches us is about scale. When you look at Andromeda, you are looking at a galaxy that contains more than 1 trillion stars. Each of those stars may have planets of its own. Each planet may have moons, mountains, oceans. And all of that, every bit of complexity and beauty, appears to us as nothing more than a faint smudge in the night sky. What does that mean? It means we are very small. Earth, with all its history, with every civilization, war, love, suffering, and joy, is just a speck of dust in a galaxy containing hundreds of billions of other stars. And our galaxy itself is only one among billions of galaxies in the observable universe. But this smallness is not something tragic. It is something astonishing. Because even though we are small, we are capable of understanding this scale. We can stand on a tiny planet, look up at the sky, and know that that faint blur is a galaxy 2.5 million light-years away. We can calculate its mass, measure its motion, and predict its future. This is one of the greatest miracles of consciousness. We are small, yet we can hold vast ideas. Inside our small heads, just a few kilograms of brain cells, we can carry a model of the entire universe. The second lesson is about time. Andromeda has existed for roughly 10 billion years. Humans have existed for only a few 100,000 years. Our civilization, with writing, cities, and technology, has appeared only within the last few thousand years. Compared to Andromeda's lifespan, the whole of human history is a single blink. That realization can make our lives feel meaningless. If we live only a few decades in a universe that lasts billions of years, does anything we do really matter? But there is another way to see it. Every moment of our lives, however brief, is unique. It will never happen again. This moment, right now, as you hear these words, as you breathe, as you exist, is precious precisely because it is fleeting. In Buddhism, there is a concept called ksana, the smallest unit of time. Each moment is an opportunity to awaken, to be present, to live fully. And when we recognize that time is limited, that we do not have an infinite number of moments, we learn to value each one we are given. Andromeda reminds us that time is a gift. And the best way to honor that gift is to live meaningfully, not only for ourselves, but for those around us, for future generations, and perhaps even for the universe itself. The third lesson is about connection. Andromeda and the Milky Way are moving toward each other. They are bound by gravity, a force that is weak yet relentless. And one day, they will merge into one. This is a beautiful metaphor for connection. In the universe, nothing is truly separate. Everything influences everything else through gravity, through light, through electromagnetic fields. The atoms in your body were forged inside stars. The oxygen you breathe was created by photosynthesis, powered by energy from the sun. The sun orbits the center of the Milky Way. The Milky Way is influenced by Andromeda. And this entire chain of connection began with the Big Bang 13.8 billion years ago. We are not isolated islands. We are nodes in a vast network of relationships. And when we truly see this, we begin to feel a sense of responsibility, not just to ourselves, but to everything that is connected to us. In quantum physics, there is a phenomenon known as quantum entanglement. Two particles can become entangled in such a way that the state of one instantly affects the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance. Perhaps, in some sense, we are all entangled. Perhaps every action we take, no matter how small, sends ripples through this web of connection, affecting people and things we will never meet. And if that is true, then every action matters. The fourth lesson is about change. Andromeda is not static. Stars are being born and dying. Planets are forming and being destroyed. Smaller satellite galaxies are being torn apart and absorbed. And eventually, Andromeda will collide with the Milky Way and become something entirely new. Nothing exists forever in a fixed form. Everything is in a constant state of transformation. This is a fundamental rule of the universe, from quantum particles to galaxies. And it applies to us as well. The cells in your body are constantly dying and being replaced. Your thoughts shift from moment to moment. The people you love change. You change. And that is not something to fear. It is the essence of life. In Western philosophy, there is a famous saying by Heraclitus, "No one ever steps into the same river twice, because the river changes, and the person stepping into it changes too. When we accept change, instead of fearing it or resisting it, we learn to live with greater flexibility and openness. We learn to let go of what has passed, welcome what is coming, and live more fully in the present moment. The fifth lesson is about beauty. Andromeda is beautiful. Not because it is perfect, but because it is complex, chaotic, and yet ordered. Its spiral arms are shaped by gravity and motion. Regions of star formation glow with the light of young stars. Dark dust clouds obscure that light, creating contrast and depth. This beauty serves no practical purpose. It does not help Andromeda survive longer. And yet, it exists. And we, through consciousness, are able to recognize and appreciate it. There is an old philosophical question: if a tree falls in a forest and no one hears it, does it make a sound? In a similar way, we might ask, if a galaxy is beautiful but no one ever sees it, is it beautiful? The answer may be that beauty exists in the relationship between the world and the observer. Andromeda has structure, light, and form. But beauty emerges when consciousness, our consciousness, encounters it and feels awe, admiration, and appreciation. So when we look at Andromeda and feel that it is beautiful, we are participating in an act of creation. We are bringing beauty into the world by recognizing it. And this is true not only for Andromeda, but for everything around us. A flower, a face, a piece of music, a mathematical equation, all of them have the potential to become beautiful when we take the time to pay attention, to be present, to truly see. The final lesson, and perhaps the most important one, is about hope. Andromeda is rushing toward us. In about 4.5 billion years, it will collide with the Milky Way. That may sound like a catastrophe, an ending. But it is not. It is a transformation. Two galaxies will merge and give rise to something new, larger, and more complex. This reminds us that endings are not always endings. Sometimes, they are simply the beginning of something new. We live in a time full of challenges. Climate change, inequality, conflict, disease. It is easy to feel despair, to believe that everything is falling apart. But when we look at Andromeda, we see a bigger picture. The universe has existed for 13.8 billion years. It has gone through countless transformations, countless endings and beginnings. And it is still here, still evolving, still creating new things, new stars, new planets, and perhaps new forms of life. We are part of that process. We are not passive observers, but active participants. Every action we take, no matter how small, contributes to the direction of the future. And when we remember that we are made of star matter, that we are built from the same atoms that make up Andromeda, that we are the way the universe becomes aware of itself, we begin to feel both responsibility and hope. A responsibility to live well, to care for this planet and the beings who share it with us. And a hope that, no matter the challenges we face, we can overcome them, not alone, but together. Because in the end, that is what Andromeda teaches us. We are not alone. We are part of something far greater, a vast and wondrous universe that is still writing its story. And we have the privilege of being part of that story. So the next time you look up at the dark night sky and see Andromeda, that faint smudge of light, remember this. You are not just looking at a galaxy. You are looking at a part of yourself, at your past, at your future, and at the endless beauty of existence. But now, after traveling through space, time, and philosophy, there is one final question left. As the universe continues to expand, as galaxies slowly drift apart, what will happen to Andromeda, to the Milky Way, and to us, in the unimaginably distant future? We know that in about 4.5 billion years, Andromeda and the Milky Way will collide. Over the next few billion years, they will merge into a single galaxy, Milkomeda. That is the near future, relatively speaking. But what happens after that? After Milkomeda has formed, after the frenzy of star formation has settled down, after the central black holes have merged. Milkomeda will endure for trillions of years. It will keep rotating, keep forming new stars, though at an ever slower pace, from the gas it still has. But eventually, that gas will run out. There will be no raw material left to make new stars. And the stars that already exist will slowly begin to die. Small stars, red dwarfs, can survive for trillions of years, burning their fuel slowly and efficiently. But even they will one day run out. They will cool, fade, and become black dwarfs, cold stellar corpses that no longer emit light. Larger stars die much sooner, ending their lives in spectacular supernova explosions, leaving behind neutron stars or black holes. These remnants, the leftovers of what were once brilliant stars, will drift through the darkness, cold and silent. Around 100 trillion years after the Big Bang, about 86 trillion years from now, the era of star formation will come to an end. No new stars will be born. The universe will enter what scientists call the degenerate era, when the only remaining light comes from cooling white dwarfs and neutron stars, and from the rare collisions between stellar remnants. But even these sources of light will fade. Around 1 quintillion years after the Big Bang, nearly all stars will be gone. The universe will be dark, cold, and almost empty. By then, Milkomeda will no longer be a shining galaxy. It will be a collection of stellar corpses, dead planets, and thin gas drifting through the dark. No light. No heat. No life, at least not life as we know it. But the story does not end there. Because even stellar remnants do not last forever. According to the laws of quantum mechanics and general relativity, black holes, despite seeming eternal, slowly evaporate. Stephen Hawking discovered that black holes emit an extremely faint form of radiation, now known as Hawking radiation. Over unimaginable spans of time, black holes gradually lose mass, releasing a dim glow, perhaps the last remaining light in the universe. And then, after an almost incomprehensible duration, even the final black hole will evaporate in a brief flash of energy and disappear. We call this phase the black hole era. And when it ends, the universe will enter its final stage, the dark era. In the dark era, the universe will be nearly empty. Only fundamental particles remain, photons, neutrinos, electrons, drifting through endlessly expanding space. The temperature of the universe approaches absolute zero. There are no structures, no complexity, no life, no consciousness. This is what physicists call the heat death of the universe. Entropy, disorder, reaches its maximum. And according to the second law of thermodynamics, once entropy is maxed out, no physical processes can occur anymore. In a sense, time itself comes to an end. It is a bleak picture. It suggests that everything we do, every effort, every creation, every love, ultimately loses all meaning. The universe forgets everything. Andromeda disappears. The Milky Way disappears. Earth, the Sun, and every trace of our existence is erased. But there are other ways to think about this. First, this ultimate future is unimaginably far away. We are talking about timescales so vast that the current age of the universe, 13.8 billion years, is little more than a blink of an eye by comparison. Between now and then, countless things could happen, things we cannot possibly predict. Life, or some form of intelligence, may find ways to survive and even thrive under extreme conditions. There may be new cycles of creation that we do not yet understand. The laws of physics as we know them may not be the full story. Second, even if the universe eventually dies, that does not make our lives meaningless. Meaning does not come from permanence. It comes from experience, from connection, from love, from creativity, things that exist in the moment, no matter how brief that moment may be. There is a Zen story about a master and a student. The student asks, if everything will eventually die and disappear, why should we try at all? The master replies, precisely because everything will die and disappear, every moment becomes infinitely precious. Third, there is a strange and beautiful possibility. Perhaps the universe does not truly end. Some speculative theories in physics suggest that the universe may go through cycles of birth and death. Each heat-death could be followed by a new Big Bang, creating a new universe with different physical laws, new opportunities for life and consciousness. Or perhaps, in the distant future, advanced intelligence will find a way to escape this universe entirely, through extra dimensions or parallel universes, and continue existing somewhere beyond our imagination. But whatever the future holds, one thing is certain. We will not be there to witness it. Humanity, if it still exists in any form, will have changed beyond recognition. And that is okay. Because the story is not about existing forever. It is about existing well, for the time we have. When you look at Andromeda, you are looking into the past, light that left it 2.5 million years ago. But you are also looking into the future. Andromeda and the Milky Way will merge. And in that new universe, there may be new stars, new planets, and perhaps, just perhaps, new forms of life, new civilizations, new minds that awaken and wonder about their place in the cosmos. And in some way, we may be part of that. Not as individuals, not as humans, but as atoms. The carbon, nitrogen, and oxygen atoms in your body will not vanish. They will be recycled, becoming part of new stars, new planets, and possibly new beings. In Buddhism, there is a concept called rebirth. Not in the literal sense of a personal soul being reborn, but in the sense that matter and energy are continuously recycled, continuously changing form. You are not a fixed thing. You are a process. You are a flow. The atoms in your body were once part of stars, planets, and other living beings. And after you die, they will continue on, becoming grass, trees, soil, water, and eventually, perhaps, part of new stars in the galaxy of Milky. So in a way, you are immortal. Not you as consciousness, memory, and personality, but you as matter, as part of the great cosmic flow. And that is a beautiful thought. It suggests that we never truly disappear. We only change form. We continue the journey, a journey with no clear beginning or end, only endless transformation. So return to Andromeda. When you look up at the night sky and see that faint smudge of light, remember this. You are looking at a part of yourself. The atoms in your body were born in stars like the ones in Andromeda. You and Andromeda share the same origin, the same Big Bang 13.8 billion years ago. And when Andromeda and the Milky Way finally merge, when all the stars, planets, and forms of life within them become one, that is not a tragic ending. It is a reunion, a return to the source. There is a line attributed to the poet Rumi, "You are not a drop in the ocean. You are the entire ocean in a single drop." You, with all your thoughts, emotions, hopes, and fears, contain the entire universe within you. You have the ability to understand galaxies, time, origins, and destinies. And that ability, the ability to be conscious, to wonder, to love, is one of the greatest miracles of the universe. So live well. Live with gratitude. Live with curiosity. Live with love. Because even if the universe ends in darkness and cold, here and now, in this moment, there is light. There is warmth. There is life. And there is you, a remarkable part of the universe becoming aware of itself. Take a deep breath. Feel the life in your body. Be grateful that you are here, at this moment, able to hear these words, able to think about Andromeda, and able to feel connected to everything that has been, everything that is, and everything that will be. That is the gift of existence. And that is enough. If this journey has brought you a little peace, a little wonder, or simply helped you relax, I would be truly grateful if you took a second to like the video and subscribe to the channel. Your support helps stories like this continue to be told, helps science and poetry meet in the same place, and helps us, the ones who love the universe, find one another in the dark. And now, I want to ask you something. Where are you right now? At what moment of the day, of the year, of your life are you hearing these words? Maybe you are lying in bed, getting ready to sleep. Maybe you are sitting by a window, looking out at the night sky. Maybe you are somewhere I could never have imagined. Wherever you are, know this, you are not alone. You are part of something vast, a universe filled with mystery and beauty. And in this moment, we are connected, through these words, through the story of Andromeda, through the shared sense of wonder we feel when we look up at the night sky. Sleep well, if this is the moment before you drift off. Have a beautiful day, if you are just beginning a new one. And whatever you are doing, remember this, you are made of star stuff. You are part of Andromeda. You are part of the universe. And the universe is very lucky to have you. I will see you again, among the stars.